Welcome back. In the last class, we analyzed couple of proton NMR spectrum, couple of proton NMR spectra, and we learned how to interpret the spectrum based on the chemical shifts, based on the intensity pattern, based on the multiplicity pattern, coupling information, varieties of information you can consider, and taking all this information into account, you are able to analyze spectra of many molecules, right from small molecules to reasonably big molecules. To make you more comfortable, let us continue with this for some time today, because we will come across with some tricky situations which I am going to tell you. Now, you look at this spectrum of this molecule. It is a proton spectrum. Now, if you look at it, how many groups are there here? There is CH3, there is CH, OH, CH2 and OH. So 1, 2, 3, 4, 5 different groups are there. Okay, there are 5 different groups of spectrum, 5 groups of protons are available here in the spectrum. Let us look at this one. There is one group here, there is one here, one here, one here. What is happening to the other one? We will see where there are other things later. Okay, now you see one more peak is coming here, which is at 7.6. This is comfortably assigned as OH peak. Okay, now we will have to make the assignment of other peaks. How do you make the assignment of other peaks? Start with CH3. This is a well-known thing which we have been doing for quite some time. Now what do you expect the pattern for the CH3? Look at this, it is attached to CH proton. That means CH3 has to be a doublet. True. See, there is one peak, and further you all know CH3 comes at a very high field in the proton NMR spectrum. So there is in the high field, you see a clear doublet. So comfortably we can say this is CH3 and it is a doublet because of its coupling to CH proton. Okay, that assignment is done. Fine. Now I will say that is CH3, and this same thing is expanded here, the same doublet, to make it clear for you. So it is a doublet. That's what is clear. You saw that. Next we will go to other thing. This CH proton is written here. This is a peak. This bunch of peaks correspond to this proton, CH proton. Why does it come? If you carefully see, this CH3 experiences coupling with CH3 protons, and it has to be a quartet. Apply 2Ni plus 1 rule. This CH, because of CH3, will be a quartet of intensity 1331. Now, in addition to that, this experiences coupling with this CH2. Another interesting thing. Because of that, this is going to be a complex pattern. I remember, I am telling you, each lane of the quartet is, I am not telling you, it is going to become a triplet. Remember my statement. I didn't say, I said because of CH3 it can be a quartet. It is a quartet, not it can be, it will be a quartet. But further, in our understanding, if it is coupled to CH2 group, each line of a quartet must be a triplet. But I am not stressing that yet. That is a different reason for it. Right now, I simply say that CH is a multiplicity pattern coming like this. Of course, one of them should be a quartet because of this. Remaining, we will see why it is coming later. You can count the number of peaks here, 2, 4, 5, 5, 10 plus 2. There are 12 peaks here. 12 peaks are coming for this. We understand why the 12 peaks are coming later. Now, coming back to this CH2. This CH2 peak, if it is coupled to CH, what is the pattern I expect? I expect this to be a doublet. That is what we have been discussing all along. But now, why it is not a doublet? What is this funny pattern we are getting? It is a different pattern we are getting. We are not getting doublet at all. What could be the reason? Okay, we'll go further. And of course, what about this 4H proton? It is somewhere there. Okay, we'll see. One of them is not seen. Only one of them is written. Otherwise, somewhere broadened out. It is far away in the spectrum. That is a not of much interest for us at the moment. Our interest lies in this CH2 peak and CH peak. Now, CH I have identified as multiplicity with 12 lines, and CH2, instead of getting a doublet, I am getting 8-line pattern. What is this 8-line pattern? We have to understand. Where do we begin? First conclusion you have to draw. If it were to be equal, if they were magnetically equivalent, chemically equivalent protons, this should have split each line of the quartet into a triplet pattern. But I did not insist on that. I didn't say that. So what do you conclude from my statement? It means I am telling these two protons are not equivalent. It is not CH2 group. They are non-equivalent protons. Oh, something interesting. Fine. I'm sorry. If they are non-equivalent protons, now can we explain this pattern? How it comes? Let us try how to do that. Let us see. If they are equivalent, you are going to apply 2Ni plus 1 rule with this. And this will be a doublet. Since it is non-equivalent, now we have 3 protons coupled. These two non-equivalent 2 protons and this one. There are 3 protons coupled. When 3 protons are coupled, what is the pattern you are expecting? And remember, they are far away separated. One group here, one group here, one group here. What is the pattern you expect for this? This is a 3 coupled spin system. We can take it as an AMX pattern. Now, we remember we analyzed the AMX. When there are 3 weakly coupled protons are there, what is the pattern we are going to expect? We said each line of the each spin or each proton of AMX will give rise to 4 peaks. That's what I said. Each line of them should give rise to 4 peaks. Now, let us try to see what are those 4 peaks, why they are coming. Now, interestingly, if I write like this, I can write the structure of this like this. See, for this one, I'll write C here, 1 proton here, and write another proton here, C, and 1 proton here. This is the structure I am going to write for this molecule. Okay, for this CH2 group and its CH. Now, I call this as A proton, I call this as M, I call this as X. And X is coming here, which is experiencing coupling with these 2 protons in addition to CH3. Very interesting, right? So, now it is a quartet. Each line of the quartet is split into a doublet. Okay? Each line of the quartet is split into a doublet because of this. And further it is split because of this proton also. As a consequence only, you are getting multiplicity like this. Otherwise, you should have get only quartet of triplets. Okay, now we counted, we have got 3 plus 5, 10 plus 10, 12 peaks we are expecting. Are we getting really 12 peaks or more? Okay, in fact, we should get 16 peaks here. How? Because this is a quartet, this one, and each line of the quartet will be a doublet because of 1 coupling. So it will be 8-line pattern, and 8 line will be further split into a doublet because of other proton. It will be 16 lines. 16 lines could be present, but we are not seeing all 16 because some of them are overlapped. Don't worry. So as a consequence, you are observing only 12 peaks. 4 of them are hidden or overlapped in one of these things. Okay, this pattern is understood. Now coming back to this, these two are non-equivalent. What do you mean by that? Non-equivalent. Now, what is the coupling we are expecting? What is the pattern we should expect? When this proton is like this proton is coupled to this proton. Look at this one. When I have, see here, and this proton, and we have this proton and this proton. Now, we have to worry about these two protons. One of this proton, when it is coupled to this, let us say, in this configuration, if I take, it is a trans configuration. It's a large coupling. I agree. It is a trans configuration with a large coupling. In addition to that, it experiences a geminal coupling. You understand? So this proton experiences a trans coupling of large value, plus it will split into a doublet because of this proton with a geminal coupling, which is smaller in strength. Where is that group? Look at it. This is a large separation here. This corresponds to this trans coupling, quite large value. And each line of this one is further split into a doublet because of this geminal coupling. Of course, there is some intensity anomaly. We have to worry about it later. We'll discuss that later when time comes at a later stage. But at the moment, you saw this one. Now, what about this proton? This experiences. Now, we analyze this one. Okay, now we have to see this one. This proton experiences when vicinal coupling of 1 plus geminal coupling. You understand? This proton experiences one vicinal coupling, one geminal coupling, and now you have to see, in this case, I have to write one of the protons. Okay, let me write like this only. It is easy to understand instead of getting confused. I wanted to write in a better way. Let us see. Doesn't matter. So one of the proton experiences of the two protons vicinal coupling and geminal coupling, and one of them experiences trans coupling and geminal coupling. So each of these two protons is split into this one, split by this one into 4-line pattern. These are because these two protons are non-equivalent. Remember, in the weakly coupled spin system, what we are seeing, this is a special example. This is clear, whereas if you want to understand this one, you have to make sure these two protons are non-equivalent. That is the condition you have to take. Otherwise, you will not be able to analyze this. We will see that much better now. There is some intensity anomaly, everything, which we have to understand why everything later. And also, clearly to say which is cis and which is trans, I don't know the frequency differences here. I do not know. And one of them experiences a trans coupling, other is a cis coupling like this. We have to see which is which and everything. I will, when I get the frequencies, I'll come back to you. But at the moment, now we come back to this molecule, similar molecule now. Look at this one. This molecule has one group of proton, 2, 3, and 4. Now there are only 4 types. What is the, how many peaks are present here? One here, one here, one here, and one here. Analysis is simpler. First, you can analyze very easily one of the peaks. What is that? OCH3. It is not coupled to any of the protons. It gives a singlet, and also we know methoxy protons comes close to 4 ppm in the chemical shift range. See, there is a near the 4 ppm, the strong peak is there with intensity 3. That means this has to be OCH3. That assignment can be done. There is no doubt about it. Next, we have to see this CH3, this H, and this H. How we are going to see the another ascend the CH3 group. In normal examples which we took earlier, What was the pattern used to see? We always took Ca3 coupled to CH2. Ca3 used to be a triplet, or it is singlet, or when it is coupled to CH, it was a doublet. It was very easy to analyze. But now, look at this in this high frequency region. I'm sorry, high field region. You are seeing a spectrum with 4 lines of equal intensity. Why this is coming? What is this peak corresponding to? You simply look at this molecule, you will understand. If this peak has doublet of a doublet, now we have, after analyzing this, we are left with only these 3. It cannot be this, because if there is a long range coupling with this one, it will be a quartet. It cannot be this, because of coupling with this will be a quartet. So there is no quartet pattern seen here, but we are seeing doublet patterns and 2 doublets, or doublet of doublets to be precise. Why is it? Then obviously it must be Ca3, this one, because this Ca3 will have one coupling with this, gives a doublet, and that doublet is split into another doublet because of this proton. See, this is a one coupling, this splits into a doublet. Doublet of this one further split into doublet because of this. As a consequence, you get 4 lines of equal intensity. So this must be CH3. You agree with me? This must be CH3, and this assignment can be done easily. Okay, now let us go to the next one. Okay, this is assigned, and this is also assigned in this case. If I remove the highlighter, you will understand more. Now this is proton 3, I will correct, because this experience is 3JHH, 1, 2 and 3. 3JHH between 2 and 3, and 4JHH between 1, 2, 3 and 4, 3 and 4 coupling. So this is 3-4 coupling, this is 2-3 coupling. So as a consequence, what is larger coupling here? This larger coupling has to be 2-3 coupling. And this further shorter coupling is there. This is 3-4 coupling. Understand? So this doublet of a doublet for methyl can be understood. So we can safely assign this group for methyl protons. Now we are left with only these 2. What are these 2? Now carefully look at it. This proton experiences a trans coupling with this, that is usually larger, and also it experiences the 3-bond coupling with CH3. You understand? This experiences trans coupling, further coupling with CH3. What about the other proton? This proton, this also experiences trans coupling with this plus 4-bond coupling with this. Now you have to use the idea of 3-bond 4-bond coupling with CH3 to make the assignment, because both these protons experience trans coupling. If one is cis and one is trans, we could distinguish by the coupling strength, but now both have the same coupling strength, both are trans. This also has a trans coupling with this also has a trans coupling with this, but this pattern will be different because of coupling with CH3. This is a 3-bond coupling, this is a 4-bond coupling with CH3. Now our assumption is, we assume 3-bond coupling between CH3 proton, and this is much larger than this one. Now how do we assign this? You'll take this one. What is this one? This I would say the proton H2. Why? It has a 3J trans coupling and CH3 coupling 4J. Okay, this is, sorry, not this is proton 4, not 2. I'm sorry, this is proton 4. When you say this is proton 4, this is a trans coupling which is quite large. Center of this to center of this is a trans coupling, and it has a 4J coupling with this CH3. So first it is going to be a doublet because of this, which is quite large coupling, and each lane of the doublet is a quartet. Understand? Each lane of the doublet becomes a quartet. As a consequence, it is going to be doublet of quartets. You understand? This is going to be doublet of quartets. Now look at this proton. This proton also has a large coupling, trans coupling. Plus it is a 3J coupling, 3J coupling between methyl and proton. Now as a consequence, there is a large coupling here between this and this. That is, should be exactly equal to this. That is a trans coupling. But further, this is a 3J coupling is quite large. So 1, 3, 3, 1. This is one peak, one peak, one peak, and one peak. These four are the quartets, and another peak of the doublet will be another quartet like this. So you got doublet of quartets again. But the quartet separation is much better here than this because it's a 3-bond coupling. This is a 4-bond coupling, which is much smaller. As a consequence, we could safely say this is proton 2, this is proton 4, this is proton 3, this is proton 1. Now it is very clear how we analyze. Taking into account the multiplicity pattern, trans coupling, we could easily analyze. Now coming back to this one. Let us see how do you assign the spectrum. How many chemical inequivalent groups are there? 1 CHO, 2, 3, 4, and 5. First, before starting the analysis, we should find out how many chemically inequivalent protons are there in the molecule. Okay. Now we'll start with one by one. This is a simple logic. This CH3, all along we have been talking. What should be this pattern? It is coupled to this CH2. So it has to be a triplet. See, this is the triplet. It is expanded here. So we know this is CH3. What other thing you can comfortably assign? And this CH2 has to be a quartet because of this. Okay. And each line of the quartet has to be a doublet. Where can you get that? See, this is quartet of, this is 4 quartets, 4 triplets are there. This is a different question. Whereas look at this pattern, this is a little bit complex pattern. I safely say initially, before confirming, let me say this must be the CH2 because it experiences quartet and each line of the quartet is a doublet and some lines overlap, and as you see, you can see doublet at the far end of the spectrum on either side, far end of this group. Let us assume that. We go further. That is done, and this is true. But not only that, interestingly, this proton experiences coupling with this also. As a consequence, long range coupling is there. It is going to be a quartet. Which proton I am talking? This proton, CH2. It is going to be a quartet because of this, and a doublet because of this, and further doublet because of a long range coupling with this. So as a consequence, this becomes quartet of doublets of a doublet. First, it is a quartet because of this, and a doublet because of this. This is a long range coupling with this proton. As a consequence, doublet of quartets be further split into another doublet, each line of that. So it is going to be a quartet of doublets of doublets. Very clearly, we could make assignment, and also is clear from the complex pattern here. That is done. What is the next one? Next one, we have to see this proton. This proton has a long range coupling, large coupling with this one. It is a doublet. Very clear. It has to be a doublet like this. This proton because of this. But remember, if you look at the CHO proton which comes downfield, this CHO is a doublet. How can this CHO is a doublet? Because it is coupled to this CH. This CHO is coupled to this CH. That means you also expect coupling of this CH with this one here also. So first it is going to be a doublet like this, and each line of this doublet is a further split doublet like this, 4-line pattern. But it is not just 4-line pattern. You have triplet for each line. Where does it come from? It is a long range coupling with this CH2. This one has a long range coupling with this coupling. As a consequence, each line of this doublet of doublet is going to be a triplet like this. This is what you are seeing. So this is proton 4. So now it is clear for you. Each proton is experiencing multiple couplings. This is experiencing coupling with this and this. Because of these two couplings, the single proton, it gives doublets of doublets, and each line of the doublet of doublet is going to be a triplet because of this, and this is the pattern you get for proton. So that is very clear for you to understand now, right? So we understood this, we understood this, we understood this, and we understood this also. So what is left out is only this. Of course, this can experience coupling with this is a doublet, and it is going to be a triplet because of this. This one, first it is going to be a doublet, and then it is going to be each line of the doublet is going to be triplet because of this proton. Now this CH proton, does it have a long range coupling? 1, 2, 3, 4 bonds coupling with CH3. Maybe it is not seen here. So that's the reason why the CH has to be only doublet of triplets. So this is proton 3. So now everything is assigned. I hope you are all with me. I hope you are not confused. Very simple. I'm going to summarize this. This is CH3, it is a triplet because of this, and this CH2 is a quartet because of this, and also each line of the quartet is a doublet because of this, and it has a long range coupling to this. As a consequence, it is going to be quartet of doublet of doublets. Now, if you come to this fourth proton, this is going to be doublet because of this, doublet of doublet because of this. This is a long range coupling with this, so it is going to be this doublet of triplet. And if you come to this proton, this is doublet because of this, and each line of the doublet is a triplet because of this, and long range coupling is not seen here. Okay, in this case. So now CHO is a doublet. All the peaks and the pattern is clearly assigned. It is clear for you now. Now this is a simple example which we were discussing earlier. Look at this molecule, the C4H6O2. These are 3 different types of protons are here, and one CH3. There are 4 protons. OCH3, I mean C double bond OCH3 is very easy to assign. It is a single peak. You get it here, and intensity is 3. It is a singlet. No doubt about it that you can assign. Now your assignment should be for these 3 protons. How do you do it? Remember, each proton is chemically independent. Let us consider one of the protons. Let us say consider this proton. This proton experiences a transcoupling with this. Transcoupling is quite large, 14 Hz. And also experiences geminal coupling with this. Geminal coupling is very small. So it must be a large doublet, and each doublet should be split into another small doublets. That has to be this. This large doublet is transcoupling, and small doublets is because of physical coupling. I would say this is this proton. This is this proton. I can assign it. Now I come to this proton. This proton has a transcoupling of 14 Hz and a cis coupling of 6 Hz. So this is a large separation of transcoupling is there, and each of them is further split into cis coupling of 6.6 Hz. So it is going to be very clear, well resolved doublets of doublets. So this I can assign for this proton. You are clearly understanding this. So this proton is assigned to this, and this is assigned to this. Now what is left? Only this. So what type of coupling this proton can experience? It can experience a vicinal coupling with this proton of 6.6 Hz and a geminal of 1.5 Hz. So this is a small spread, a small first doublet of 6.6 Hz and further doublet of doublet because of geminal coupling, and this type of pattern can be assigned to this proton. You understand how to do that? So now what I showed you is a simple molecule utilizing the idea that trans coupling is larger than cis coupling, which is larger than geminal coupling. I looking at the pattern of the spectrum, all the three protons are inequivalent. I could make the assignments very easily. This is why I was telling you when I was discussing about couplings, trans coupling is always larger than cis. You remember varieties of times, many number of times I told you varieties of examples. This is the reason. Those ideas will come into practice for you when you want to analyze this thing, such spectra. You can use those ideas. So this is the next simple example. This is a perfect symmetry is there in this molecule. So as a consequence, 1, 2, 3, and there are only 4 types of protons are present. This is nothing great. You can easily analyze, very easily you can analyze. This is CH3, a triplet, very clear. This is CH2, is a quartet. Where do you see that quartet? This one. Now our problem is to assign this to. What is 3? 3 is split by CH2 into a triplet. I understand. What about 4? 4 experiences coupling with this and also this. Remember, in the chemically magnetically equivalent case, I was telling there is a n plus 1 rule exception. These two do not couple, but does not mean it should not couple to this. It is coupled to this. As a consequence, it is going to be triplet of a triplet, a funny pattern if you expand. You get 1 3 1 triplet, 1 3 1 triplet, and 1 3 1 triplet. They overlap, and you get a pattern like this. So, very clearly, simple molecule, we can start analyzing this by just looking at the pattern. Now, we will take another example where in the proton spectrum, coupling to a different nuclei come into picture. Get my point? Coupling to a different nuclei will come into the picture. That is heteronuclear coupling. But remember, this resonance is not seen here. That is seen only in the fluorine resonance. But you are getting the proton spectrum, you have to focus only on this proton, and this proton, and this proton. So there are 3 groups of peaks, 1, 2, and 3. That's all. And then, but coupling, this is a passive spin. But coupling between for each of the chemical sheet position which are active spins, coupling to passive fluorine is present. Remember, and I am seeing here proton 1, you get 1 2 coupling, 1 3 coupling, 1 4 coupling, all are passive spins. When I see proton 2, this is active spin, I get 1 2 coupling, 2 3 coupling, and 2 and fluorine coupling. Similarly, when I see 3, I get 3F coupling, 3 2 coupling, and 3 1 coupling, all are seen. So coupling to fluorine is visible in the spectrum. Don't forget that point. With that, now we have to analyze. Let us look at the assignment. First one, I will say this is 3. I made this assignment very simple for you to look at it. Why? Why I said it is 3. Remember, this one of the fluorine, let us say fluorine coupling, this is fluorine, this is proton. Thus, this fluorine will have 3 bond, meta coupling to this proton. Similarly, this proton has meta coupling to this proton. But the coupling strength need not be same. The coupling strength could be different. As a consequence, what happens is, first this splits this into a doublet, further this splits this into a doublet. So you are going to get doublet of doublets. They because of different coupling strength. Then you may ask me what happened to this proton? A 5 bond coupling, para coupling could be there. But remember, I told you the para couplings are very small, of the order of 0.5 Hertz. That's why sometimes you see, sometimes you don't see. That's the reason why you are not seeing that. Now, what is the next one? Next one, I will say this is 2. Why this is 2? You must understand why this is 2. It's a very simple case. Look at this one. This proton experiences the coupling with this one, ortho coupling, which is a large coupling of 8 Hertz. Then it experiences the meta coupling with this fluorine and meta coupling with this proton. So each line of the doublet will become doublet of doublets. First, it is a doublet because of these 2 lines, and each line is going to be 4 lines, doublet of doublets because of this. You are understanding my point very clearly. Please remember, this proton is going to be a doublet because of this ortho coupling to this proton. So we write 1 doublet. Now what is going to happen? This is going to be split into doublet because of this. Okay, I'll write like this. It is also going to be split into doublet, each line of this because of this. 8 lines. See, you are getting 8 lines here. Count it. you can get 8 lines. So you can measure which is which and analyze, and you get 8 lines for this. That's why this is a proton 2. Now what is left for you is proton 1. Okay, assignment is easy. But why it is a triplet? Look at it carefully. This can experience coupling with this proton and also this fluorine. When the couplings are nearly same, it appears as if it is a doublet of doublet. It is not equivalent spin, so it is doublet. It is not triplet. It is doublet of doublet, but two lines of this peak, central peak, overlap because of nearly equal coupling. As a consequence, this appears as a triplet-like pattern. It is not triplet. It is doublet of doublet with two lines, central lines overlap. Then what happened to this coupling? Long range coupling you don't see. I told you, in this case we didn't see this 1-3 coupling. Consequently, when you observe 3, you don't see 3-1 coupling. So that's what happens. So assignment have become very clear for you now with this. I hope you are all with me. I took several examples here, simple molecules to analyze. Based on the multiplicity pattern, I also took heteronuclear coupling so that you will know the heteronuclear being present, coupling will always be there. But what happens if I see fluorine resonance? You get only one peak, one chemical shift, only one fluorine is there. But there is a splitting because of this and this. Very easy then to analyze. This is a doublet because of this, a doublet of doublet because of this, and doublet of doublet because of this. So if you see the fluorine resonance similar to this, you will get 8 peaks. And you can analyze that and get all the 3 couplings with that. So, okay. So, what I'm going to do is I will give another simple example of the heteronuclear coupling. I will not do this. We'll come to that later. I'll give you a trick of the example how sometimes spin system gets simplified because of symmetry. Look at this molecule and this molecule. Now the possibility is in this case, it could be this conformation or this conformation. We do not know. Okay, cis or trans. It is there what they call a cis or trans here. If it is cis, you get one type of spectrum. If it is trans, you get another type of spectrum. But how do you identify that? If it is cis, it is a A2X3 spin system. If it is trans, it is going to be these two will non-equivalent. It is ABX3 spin system. So the conformation of the molecule, if you look at it, you can looking at the spectrum, you can also say whether it is equivalent or non-equivalent, whether cis or trans. Okay, that is the way this in the ABX3 case, this AB pattern, you are going to get 4 quartets. Very easily you can see that. I give you another simple example in a molecule like this, a 3-fluoropropanol. Okay, if I start analyzing that spectrum, it is going to take more time. What I will do is I will stop today at this place. I have given you some gist of various examples, and next class I will take you to heteronuclear analysis like carbon 30 spectra, heteronuclear spectra, heteronuclear coupling constitution, etc. I am going to introduce. So next class I will give you one simple example of the proton spectrum with the different heteronuclear couplings, and then straight away we go to analysis of the heteronuclear spectra and other ideas.